Okay, so now let's talk about voltage. As I said, I like what your book is talking about, so we'll use that as a reference a little bit. So, one of the things that it is trying to say is that voltage is a measure of how much. So, there are two, three terms, first of all, right? Let's talk about those first. So, voltage, potential, difference, and then finally EMF, and all these, or maybe also called maybe volts, like we just say that okay, how many volts is this, right? All of them are nearly the same thing, and what we'll try to do is try to understand the difference between these. Okay, so voltage, so we said that in a wire we have charges flowing, right? So who makes the charges flow? Who is giving this energy? Who is pushing in this first electron? Someone needs to push, and then an electron pops out from here, right? And this so someone needs to give the energy, and of course that pusher is the battery. So battery provides some energy. So it provides an energy plus. It's very high in energy right now. At some point in the middle, the energy is only like maybe reduced a little bit, and at this point, maybe energy then again becomes zero. So those electrons come back to the battery and be like, oh, I'm done with energy. So give me more energy. So that just recharges them. And then it comes here and then it slowly decreases energy through collisions and for so on and so forth. You enter with a lot of energy, but you realize that okay, there's no space to move inside the wire. So you just collide and then you struggle your way through. So you keep on losing energy and then finally you get out with zero energy. At the end of the wire, you're like, okay, finally I'm home. And then you do this all again and again. Now, this energy that is given is called potential difference. So this is the potential. So let's be a little more precise, right? So we say that energy given in is called EMF, like the battery's EMF, and the energy consumed is the potential. So if there are say two wires, like it is in the case of your book, what they're doing is, see, there are two consumers of this thing. So the charge that comes out from here, so gets like some amount of tired here by the time it crosses the first register, and it gets extremely tired, like zero tired at this point, and then the battery again pushes it through, and then it moves and then gets a little bit tired, gets fully exhausted, and then keeps going, right? So because it gets more exhausted here, so the potential difference across this must be more. So the way that they describe it is, if it was given 12 joules of energy and 1 coulomb current was flowing, then 8 joules of those energy that you were given is lost here, and 4 joules were lost here. So these numbers shown in blue are potential differences, and the number shown right here is the EMF of this guy, which is the energy provided. So we need to understand this very carefully, and but once you understand this, we should be good. So potential difference is in terms of energy. It is defined. We said so. It is just energy transferred per unit charge. So every charge, for one charge, how much energy you are putting in. So if there are say there are 5 electrons that have left here, you need to supply 12 into 5 joules, right? But the potential difference, we don't want to say that is 60 volts. We just say that it is 12 volts. So every electron gets 12 joules of energy when it goes. Every 1 coulomb of charge gets, because this is 1 coulomb, so it will be like a lot many more electrons. But that's okay. But like 1 coulomb is equal to a million electrons. That's a lot of electrons. So a million electrons get 12 joules of energy in total uh, by the battery. Okay, a little bit confusing, but just go through this section once. I'm sure you'll get it. So let's also try to recreate this circuit, right? Like what they are trying to do here. So let's try to do a simulation. Yeah, so right here, so we have a battery. So let's keep this as a reference side pay. This on the side and this on the other side. So let's see. So we have a battery and the battery voltage is 12 volts, right? So this is the 12 volts battery that we have connected. We need to have two resistors. So for this resistor, the resistance is 20 ohms. So resistor is anything that is just opposing the flow of electricity, you know. This you're sure about, right? It just like, so higher the resistor, it's like more you get tired running through it. So we'll just talk about it a little bit. So this is already 10 and this is 20. So these two are done. And now we connect them through a wire. This is a wire. Then you have a wire here. And then finally, as soon as the circuit is completed, they start flowing, right? So now we can also measure the voltage differences that they were talking about. So on the positive end goes the positive end, on the negative end goes the negative end, and you get a voltage reading of 12, right? Which is this guy right here. So that means the electrons that are going this way, let's say it in the opposite direction of current. Let's say the current charge carriers, which are opposite of electrons, are have 12 joules of energy right here when they leave. Now this goes up and right till here. So then we see that, oh, look, it has lost 4 electrons. It is minus 4, right? And then you can keep on moving further, right? So it becomes, so it loses more 8 volts here. So 4 volts right here and 8 volts here, and then finally you have lost all of the all of the energy that you had gained by this time, right? And so at this point you need to be again be filled in with 12 joules, and then you will keep going around just like that, right? So this is what this we are talking about here. So again, one thing that we see, that if we increase the voltages maybe to a higher voltage, you see that the just this is all going very fast now, because we studied last time in the last video that the current will be proportional, their velocity will be proportional to the current. So we see that velocity of all of them are higher because the current is higher. Okay, let's make this back to 20 volts and 12 volts. Okay, awesome. If this is clear, let's go back and let's continue with our analysis. So we are done with voltages. So the next topic that we're going to talk about now will be resistance. So resistance we have already lightly talked about. So we know that when we increase voltage, then current increases, right? So there must be some like proportionality constant which describes this. So we just say that that proportionality constant is V equal to IR. So that means, like, say you have provided 1 volts and you want 1 ampere of current, then you need 1 ohm of this thing. If you have provided 2 volts, then you will, from the same this thing, you will get 2 amperes of current. So this is like a constant that tells you that, okay, what should the number here be for this guy right here. So if you say make this 10 volts, so how much will this be if this is 1 ohm, right? So you can work that out. So this number kind of helps you to convert between this and this. So which is why this is called like a proportionality constant. So like basically I was proportional to V. So we needed to remove this and we just removed it and it converted to a equal symbol. And then we added this resistance symbol right here. Right. So on a physical sense, it describes what we already talked about. It is this resistance to flow, right? So we see that, so if I tries to say decrease the resistance, so so this I've already decreased, so you can see that it has gotten a little bit faster. Maybe let me try to reduce this, so it gets even more faster, right? So the idea is a resistance tries to oppose the change. So if I keep a very high resistance, it is moving very, very slowly. So there is a very high resistance to it. So the amount of energy that you're providing can only cause so slow of a movement. Okay. So this is good. If you understand this, let's keep moving. Again, all of these are small ideas, but you need to understand them. Okay, so the last thing that we're going to talk about is what we call uh, electric power. Okay, P. And that electric power is nothing but it's given by whatever energy is being transferred per unit time, right? We have already defined this earlier, is energy by time. Energy, luckily we are in luck, is we already know is the amount of work done, right? And amount of work done we have already figured out from a previous potential discussion is potential difference into the amount of charge that was given. That will be the work done, right? So per charge you are giving 12 joules. So if there are 5 charges, then it's 5 into 12. That's the amount of work that is totally done by time, right? And this unit right here, like the second quantity, is called current. And then we are done. So potential is equal to V by I. So this is power. Sorry, this is not potential. This power is equal to V into I, which is also given as I square R. Like if we replace V equal to IR here, then we get I square R, or we can directly get V square by R also. If we replace I as V by R, right? So all of these are power formulas. Like we'll use them in different contexts when we do problems, but then this is what you need to know. So let's just do a quick summary before we stop of the all the formulas that we saw today. So the first thing that we saw is current is NEAV, right? I'm not giving you context, it's just a wire that has a drift velocity of V, right? An area of A, and a number density inside it of N. If this is the case, then the net current flowing through that thing will be NEAV, right? The next formula that we studied after this was that I is primarily defined as flow of charge per unit time. So this is a very basic formula. Then we got on to voltages. We said voltage is this concept of a work done, but per unit charge. So for every charge, whatever work you have to do is called voltage. So if there are 5 charges and then you have to do 60 joules of work, then per charge you are doing 12 joules. So this is the definition of voltage, right? Then from these discussion, we also said that we also then defined resistance, and then resistance was defined as if you increase voltage, then current increases. So there must be some number that helps us, like just plug in the number and get to find it. So we called it the proportionality constant, right? And then combining these two ideas, finally we got the power formula, which was I into R, sorry, V into I, which was also given as I square R, which is also given as V square by R, right? So all of these formulas you need to understand and keep them in mind. I'm just giving you a list here so that you just have things straight in your head, right? Okay, if this is clear, this is good. Let's stop. I'll see you next time.